this is a dissection kit, and the link between me and this dissection kit is the kit belonged to Eileen Furlong. And Eileen went on to become probably the most successful Irish scientist of our generation. And it's a circular story, I suppose. I inherited her dissection kit after she left the lab, and Fidian went on to become my mentor. And, 20 years later, I find myself coming back to think about Eileen a lot and what she does in her job because of the impact that her work has had subsequently on ours.
So what do you use the dissection kit for?
I still use it now in pharmacology practicals.
And what's in it? Like there's scissors and what are the paintbrushes for?
So they're for when you're making sort of glass slides and sections and things where you might need to just tidy up around the edges. Like when you buy the kits, they've got all these funny things in them that aren't used for. I would say that if you were to ask me which ones will I use, for example, in my dissections, really the scissors and the probe are probably all you need.
But it's nice to have the fancy bag. What is your name? Who are you?
My name's John Crean, and I'm a pharmacologist. I trained initially as a biochemist, but I kind of masquerade as a stem cell biologist.
So what's this?
This is a bioreactor, a plastic disposable bioreactor. You're supposed to throw them away after one use, but we wash them and reuse them a number of times. So one of the great ideas, I suppose, is that instead of using animals for testing drugs, that we can use organotypic stem cell derived materials that look like and behave like animal tissues or human tissues. And that's what we do with these. We take stem cells and we specify those stem cells. And what that means is we just use a very small set of biochemical cues to tell that stem cell to become something else. And the something else that it becomes is user-defined. So I know it sounds kind of strange, but it's now within our capacity to mimic the development of nearly every organ in the human body. In the ultimate fantasy, of course, is the issue of growing something that can be used as replacement tissue. And earlier, or I should say later last year, in December last year, the very first successful transplantation of stem cell derived islets from the pancreas were implanted into a very lucky middle-aged type 1 diabetic in New York, and he's now walking around quite happily with his stem cell derived islets, providing, I believe, 90% of his daily insulin requirement, which means that ostensibly in this particular patient that they've cured his type 1 diabetes.
Remarkable.
Yeah.
Completely incredible.
And even now saying it, when I say it, tell students and tell my friends and tell my colleagues, everything got subsumed into the pandemic, didn't it? That we sort of miss these monumental breakthroughs. And when you hear about it, you go, did they cure diabetes? I said, well, they haven't cured diabetes, but they've cured one person's diabetes. And that's a great place to start.
So you are actually in your lab here in UCD growing, using this bioreactor here, or something like it, growing small organoids. And I've actually seen them. When I say small, they're really tiny. Organoids of different tissues.
Yeah.
And they contain all the different cell types that might be in a kidney, for example.
That's exactly it.
Yeah.
So, of course, most organs are very complex because they have many different cell types. And up until now, it's been very difficult to model anything on an organ level because of this complexity. But advances in techniques and technologies have meant that you can take very complex multicellular organs and do experiments on those organs that previously we wouldn't have been able to do. So you can look at gene expression at the level of an individual cell, whereas previously it would have been gene expression at the level of an individual organ, if you like. So it means that the heterogeneity within an organoid becomes an advantage rather than a disadvantage. The fact that there are multiple cells there, multiple cell types, means that in effect you can carry out an experiment or you can mimic disease in which all of the cells track what is happening to every cell at the same time, which is really fantastic.
It's incredible. Now, you said at the beginning there, you casually mentioned that these organoids are stem cell derived. What does that mean?
Right, so the starting material are stem cells.
And what are stem cells?
So I suppose the best way to think about a stem cell is as an open template, a cell that has the capacity to differentiate into any other cell in the body. They maintain themselves within this state of stemness by a very sort of clever self-sustaining trick in which, in the absence of a differentiation signal, the cells retain their phenotype, that is, they don't differentiate. So, for example, in the fertilized embryo, those cells are what we would refer to initially as totipotent, and then they go through, which means that
they can become any. Yeah.
The totality of potency, as it were. Yeah. And then pluripotent is as they differentiate, so as the first stages of differentiation take place, they lose some of that capacity. And then as the cells become the different organs of the body, they become what we used to refer to as terminally differentiated. And for a long period of time, it was our understanding that cells followed this pathway in a single direction, that they went from a stem cell, an embryo, to a differentiated tissue like a muscle or skin or eye or brain. Now, about, I suppose 10 years ago, 2006, a very clever scientist and modern day hero figured out a way in which you can reprogram an adult cell so that it acquires this state of stemness.
So that's remarkable. You're actually, that discovery means that you can actually sort of turn the clock back.
That's exactly it.
Which is why I have this watch here on the table, that we have this idea that development and that life goes in a direction, but that this discovery means that actually it's possible to turn the clock back and bring a cell that's a liver cell or a kidney cell back to being a stem cell, or to having some stemness, stem-like.
Stemness. It's a really good word, because I think we call it reprogramming. The technique that we used was developed by, as I said, my hero, Shinya Yamanaka, who subsequently won the Nobel Prize for discovering this technique. It's very, very simple, very, very beautiful and elegant, and involves a very small number of factors, which was, I think, the most remarkable thing.
When you say factors, you mean literally like substances that you apply or add?
That's a good way of looking at it, yeah. I mean, they're actually proteins, transcription factors. And the technique of adding we would call overexpression in this case, but it only required ultimately 3 factors to facilitate the acquisition of stemness. So you could take a terminally differentiated cell and turn it back into something that had plasticity. So it's like reversing the developmental process.